I mean, it's not really relevant to the course. It's true, but it's not really relevant. Okay. So we've talked a couple of times about this astm A106, and I finally have the sample to discuss some of the hydrostatic testing. Not for the one that occurred at the oil refinery where they bought 600 lengths of pipe, but if you remember, astm A106 for a piece of pipe allows hydrostatic testing. Okay, you can just pressurize the pipe with water to 50, 60, 70% of the yield strength of the material. If it doesn't burst open, it's good. And that's actually called proof testing. And if you do it on every piece of pipe, which they do according to astm A106, you have to do it according to the standard unless you say, as the purchaser, you don't want it. And then they have to mark it that it hasn't been done. Okay? Well, most of the pipe gets done, and so this, and the alternative to hydrostatic testing testing is the standard approach. You can specify the pressure you want, and typically you might specify a pressure that's 25 or 50% above your expected operating pressure. So if you're going to operate at 1,000 psi of whatever it is, gas, oil, whatever, you might test it at 1,500 psi. And so if it survived 1,500 psi, it's unlikely that it's going to fail at 1,000 psi, right? Because you overstressed it 50%. And if you go through fracture mechanics, a 50% overstress is basically, you kind of square that, and it's about a factor of 2 safety in terms of goes as a square root of the crack length. So if there is a flaw there, you should have detected the flaw within a factor of 2 of stress. Okay, not stress, but of safety factor, so far as that goes. Anyway, this is a story about a pipe, this pipe, that went through an American steel mill. It's a seamless pipe, so it could have been sold under ASTM A106. I don't remember if it was or not. It could have been sold as an API pipe, because they have standards for pipe. In fact, I think it was sold as an API pipe. In fact, now as I think about it, I know it was. But it's actually the same pipe, comes out of the same mill. It could be, they make it the same way, but it's just a question of which standard they measure it to. And the standards are uniform enough between API and ASTM that the mill, basically, whatever they got out there in the yard, it will probably meet both specs. And so they can sell it to either one. And sometimes people say they want it to meet both specs if you want to pay extra. Okay. In any case, what they do at the mill, this is seamless pipe, and so they basically take a big piece of steel that they've made, and they heat it up to about 2,200 degrees Fahrenheit. It melts at 2,600, so it's really getting not quite white hot, but very, very yellow. And they basically take a cold mandrel and they just push it right through there. It's pretty interesting to see. The mandrel is about 60 feet long, and you end up making a piece of pipe that eventually, after you cut off the ends and throw them away, is about a 40-foot length of pipe. Okay, and you can get pipe. This was, I think, 6-inch or 8-inch in diameter or something. You can get them 20, 30 inches. Well, probably 20 inches, probably the largest for a seamless pipe. If you start getting much above 10 inches, it becomes cheaper to roll it and weld it, okay, make welded pipe. In any case, to test it, they go in and they grab it with this automatic jaws at each end. They fill it with water first, and they actually do both the non-destructive electric test and the hydrostatic test on all these pipes. It's just easier to manufacture that way. They fill it up, and except for the last 18 inches where they grabbed it, they have an automatic ultrasonic test. So, you know, there's no one even, I mean, there has to be an operator to set it up, but it basically just automated, and they do an ultrasonic test through the water to see if there's any defect in the pipe. Since they couldn't measure the last 18 inches of pipe, they have a bunch of lowly paid, most of them people who can't speak English as a first language, employees that are doing magnetic particle testing by hand, where you've got basically got an ultraviolet light, and you magnetize the pipe by putting some electric current through it. If there's a flaw or a defect, it'll have a magnetic anomaly, and you put some magnetized iron oxide powder, magnetite, in there and see that fluoresces in the black light, and you see if you have a flaw. And so these guys have these little, actually they're just plastic tubes that have some of the powder on there, and they pour some in there, and they look in there with their light, and they do all this they look for second and a half, okay? But they're used to doing this all day. It's pretty boring work. It's not automated, and sometimes people will miss something, okay? But they're checking the last 18 inches of the pipe, right?
So the pipe manufacturer generates only surface flaws?
Oh no, it'll Magnaflux. They Magnaflux the outside, and they also Magnaflux the inside. The outside's easy to Magnaflux.
In the thickness, there generally aren't any flaws.
Oh, you're right. Through the thickness, there can be flaws, but they're going to later hydrostatic test this. And see, it keeps on going down the line, and then they do a hydrostatic test at whatever the pressure they want to do. But still, the ends are kind of the problem, because even in the hydrostatic test, you have to grab it by the ends and make the seal. Now, sometimes people will cut off the ends, but most of the time they don't, after they've done all this testing. Sometimes the problems occur at the end. And this oil refinery, the pipe that had the leak, it was on the end. The leak they found was on the end. Because all this other testing is probably going to, you've got a stress test, the hydrostatic test, you got magnetic particle on the end, you got ultrasonic in the middle. All this testing has a high probability of finding something, but the probability is never 1. There's always something that might get through. So out of these 600 pipes at this oil refinery they were building, they found 1 pipe, and they condemned all the rest, all the 599 brothers and sisters, and they said, we want our money back, okay? Which was not the appropriate way to handle that problem. But this other pipe, this one, got through the mill, and it went through, first of all, they took off all the identification, okay? Because they wanted to coat it. This was going to be buried in the Gulf of Mexico. So they coated it for corrosion resistance, and to do that, they had to sandblast it and apply this epoxy paint and stuff coating on the outside. Then they buried it in the Gulf of Mexico. This was going to be a pipe to bring the oil from a production platform onshore, so they didn't have to have ships shuttling back and forth full of oil, right? And when they pressure tested it, when it was in service, they were actually pressure testing at like 3,400 psi rather than the 3,500 that they had done at the mill. Well, it turns out it started to leak. And now the problem is it costs a lot more to repair it when it's down buried a couple hundred feet in the Gulf of Mexico. It was a couple of thousand feet in the Gulf of Mexico, in which case it might have been cheaper just to abandon the whole pipeline that you had just built at a cost of $50 million or something. This one only cost $5 million to recover the pipe and replace it after it had already been buried in the ground, okay? So people weren't happy, and they sued each other and whatnot. Anyway, when they got it up, here's the defect. I'll pass it around. You can see this gouge in here. And if you look at it and think about it, how could you form something like that? Well, what happened is the mandrel, the steel mandrel that pierced to make the tube, probably had a fatigue crack on the end, and a piece broke off inside this thing as it's piercing it, and just rolled that piece of cold steel into the hot steel. And in fact, we confirmed that. We cut out a little section, did some metallography, found it was decarburized on the surface, okay, which means it had to have been hot at some point in its life, and the only time it had been hot at some point in its life, the last time it had been hot was when it was being pierced. And that was, you get decarburization at high temperatures because you're burning the carbon out of the steel, and so we knew it was a steel defect. However, that actually goes through more than 80% through the wall. And some people say, well, it couldn't have been there present at the steel mill, because how could it have supported the stress? Because 3,500 psi was like 50 or 60% of the maximum capability of that pipe. Well, it turns out It's not oriented in the proper orientation, okay? It's not infinitely long. The calculation these people are doing assumes that you have an infinitely long axial, perfectly axial crack. If you actually do a finite element analysis on that flaw, you'd find that it would take right around 3,500 psi to fracture it. Okay, so a more sophisticated stress analysis says it was right on the edge. If it had been a little bit worse, a little bit bigger defect, the hydrostatic test would have found it at the mill. It never would have been shipped. If it had been a little bit smaller, it'd be in service in the Gulf of Mexico today. It just happened to be just the right size to fail at just the wrong time in the second hydro test. Okay? So, in any case, however, the company that had manufactured is doing everything to say, well, it's not our pipe. You can't prove it's our pipe. You eliminated all the identification on the pipe when you coated it down in Houston. Okay? You took off all our markings if it was our pipe, and you can't prove it's our pipe. A piece of steel is a piece of steel. No one can tell the difference. Well, not exactly. As they say, it hurts. Turns out, even in carbon steel, there are probably about 10 different elements that are markers. What are the elements in steel? Carbon, manganese. Iron's probably not the easiest one to tell the difference because there's a lot of iron in all steel. Okay, carbon, manganese, silicon, sulfur, phosphorus, which are impurities. There might be some residual nickel or copper. There's a whole bunch of things, probably 8 or 10. And so what we did, there is data out there. It's amazing if you go looking. And now that we have, I had these actually. This is a 1984 issue from the American Iron and Steel Institute. Not that you need to read this, but it's started out in September '74 and 1984. They updated it. The variation of product analysis and tensile properties, carbon steel plates and wide flange shapes. Well, this wasn't a plate or a wide flange shape, but it is carbon steel. And product analysis is how much variation you have in different things like the carbon content. So the steel companies looking at different levels of carbon, different thicknesses of product, hundreds and thousands of tests, looked at the statistics. Here's the standard deviation, and it's 0.15% carbon plus or minus 5 to 7 thousandths, okay, on the carbon. So there's a distribution for the carbon content. And so if you look at that Gaussian distribution for carbon, and you look at another one for manganese and another one for phosphorus and sulfur and silicon on the next page and keep on going, and we didn't just use this one source, but the steel composition is actually a fingerprint. And we knew what the heat analysis was at the steel mill as reported by the steel mill for this amount of pipe that they'd purchased. And we compared that, and then we showed that within 1 chance in 100 million, this had been made at this plant, okay, and conformed to this heat that had been purchased by the oil company from the steel company. So that argument kind of went away when you start getting down to statistics of 1 in 100 million. Most people would say that's pretty good assurance that it really was the same piece of pipe. But then we got into the argument of how could it have passed the hydro test and everything else. Well, it passes the hydro test because it was just the right size. This was the mama bear crack or defect, okay? If it had been daddy bear or papa bear or baby bear, it would have been okay. So that's just sort of another case study of hydro testing and what can go wrong and what can go right. You never have 100% assurance on anything when you're manufacturing. You try to do the best you can, but there's still going to be mistakes that get through. So let me spend a little bit of time just talking about safety factors. Dr. Belmar's been talking about it, but I wanted to kind of go over some of the typical types of safety factors and where they come from. If we look at the structural welding code, AWS D11, which is bridges and buildings, turns out for buildings, the safety factor is 1.67. That's historical safety factor. People have found for statically loaded steel structures, 1.67 is a good number. Okay? For bridges, it's a different chapter in the code because the bridges are fatigue loaded. It's 2.0. And we mentioned the other day, when at the end of Dr. Belmar's lecture, he put up the stress strain curve for fatigue. This is stress versus log of cycles, and you come down like this. When you get to about 50% of your yield stress, essentially the fatigue life in steel goes out, and we call it the fatigue limit. And the life is infinite in fatigue, and that's why if you have a 2.0 safety factor and you never go to more than half of your allowable stress, or not your allowable stress, but your capacity stress, your yield strength, you shouldn't get fatigue cracks, all other things being equal. Turns out for welds, most welds, the safety factor is 3.3. And that, again, is historical, but you're going to produce defects at welds. You're going to have, welds are located at the most highly stressed locations, the corners. They create notches, toe of the weld, and things like that. And people just found that that safety factor on the weld is usually sufficient that you won't get failures at the weld, okay? Unless you have really big defects in the welds. So this is experience. This one, you actually can look at some scientific stress strain curve, and this is sort of experience, and that's where they come from. Now, the problem with these buildings, and I think I mentioned it briefly before, that's what the code says. And you remember Dr. Belmar was talking about the tongue on his trailer, and he said he wanted to make it 15 feet long rather than 12-foot long beam, but he wanted to keep the weight down, so he actually shaved it down and made it a smaller beam in the last 3 feet and take some weight out of it. He also mentioned, just in passing, he put a doubler plate back where the beam is welded to the crossbar. Okay? That's because you need more stress there. You have more stress there. The stress concentration where the beam connects to the crossbar, you have higher stress. It's the maximum bending moment. And so you put a doubler plate on top and you strengthen it there. Well, back in the early to mid 80s, the people who made prefabricated buildings decided that computers were getting good enough that these civil engineers could design beams and put doubler plates on beams, so that if I got a roof joist, and a roof joist looks something like this, and it has stiffeners in between, like this, that you actually need a lot of, out here where you have your maximum bending moments, you need more thickness here than you do out here at the ends where it's right on support. In fact, you can tell you don't need the same thickness. This is where it's going to be supported on some column. And you don't even have to have the big depth that you get for the stiffness of these supports out here when you're right next to the thing. The big bending moment's right in the middle. If you put weight on this, you'd see it sagging most in the middle. But that's where you need extra metal there. You don't need as much metal here. But for years, we've just been making beams uniform thickness and length because that's the way they come off the rolling mill. And even when they built these beams up, that's the way they did it. But with automated cutting technology, we could cut all kinds of shapes in the computer without a lot of labor. With improved welding processes, we could weld it together. And they decided they could start designing these beams for minimum weight and meet the 1.67 safety factor. So the real safety factor in the past was not really 1.67 that we had developed our experience on. In most cases, it was more like a 2.0 safety factor, even for buildings, because we were always using more material than we really needed to. But these guys decided, okay, we're going to be able to calculate exactly how much steel we need, and we'll put it where we want, and we can get 30% of the weight out of these things, and that's a huge profit to get a lot of your steel out of that. So that's what they started doing. Now the problem with computers in the mid-80s, you know, an IBM PC might have a 20 megabyte hard drive. You know, it was this big, right? Now we talk about, you know, a terabyte. It costs, I just bought a terabyte for $100, right? I remember my original 10 megabyte hard drive in the late 70s. It was this big around, okay, 10 megabytes. This was a DEC digital equipment, PDP 1123. So things had improved quite a bit, but by the mid 80s, they still didn't have enough capacity to do things that weren't symmetric. So they designed everything as if the building was perfectly erected. And everything was fine until the big snowstorm of 1988, I think it was. Okay. No, 79 was here. This was one, they had a huge snowstorm. It was the storm of the century, and it came right up through Princeton, New Jersey and stuff, and it just, buildings were collapsing all over New Jersey and eastern Pennsylvania, okay, because they had bigger snow loads than they were used to having. Now, so far as the snow loads had been built up from historical experience. And one little township might have a 28 pound per square foot snow load, another one might have 35. It depends on how much snow they got in their local region. And so those standards are actually by township almost, okay, what the snow load is. And then people started getting in arguments about, well, we exceeded the snow load, oh no we didn't, you know. But what it really turned out in a lot of cases is these things had been designed to 1.67, which was what the code said, but the code had been built up at a time when you couldn't do all this optimization. And the real standard was actually significantly greater than 1.67. So today with computer technology, it's done wonders, but it's also shaved the safety factors down to the bare minimum in many cases. The bare minimum that was built up where it was just sort of a guideline before, and we always exceeded it by 20–30%. And so what's happened is we've been shaving the guideline all along. What happened with AWS D12, which is the aluminum code, it turns out the metallurgy of aluminum is much more complex, and they have heat-treated alloys. Steel has heat-treated alloys, but mostly we're not heat-treated fancy steels for structures. But the aluminum structural welding code has safety factors of 2 to 4, depending on the alloy. You'll have a different safety factor in the code, and that's why that aluminum design manual, someone asked me one day, and I just happened to have the old 1997 AWS D12, and I had the smaller 2003 version, but in between there was the 2000 aluminum design manual, okay, and it's that thick. Well, what happened is, because of all these changes, they used to have big safety factors. Now they're getting down so specific that there's a different safety factor for each alloy or each group of alloys. So this is one of the reasons codes and standards are proliferating in size. The fatigue strength, okay, there is no fatigue limit for aluminum alloys. In aluminum alloys, this thing doesn't become horizontal, it just keeps going down. And they've measured it out to 10⁸ cycles. Okay, I think I've seen some data going out close to several times 10 to the 8th cycles. You start figuring out what 10 to the 8th cycles is in seconds. There's about, what is it? There's 8,000 hours in a year. So there's about 10 to the 7th seconds in a year. So if you go 10 to the 8th cycles, that would be a 10-year fatigue test at 1 cycle per second. Now, in fact, when they do a lot of these tests, they'll actually do it in a very high-speed vibrating machine, and they might do it at 100 hertz. The problem with doing a fatigue test at 100 hertz, you're actually putting enough elastic energy in there that you have to be careful that you don't overheat your sample. And you're now doing a hot test, okay, rather than a room temperature test. But nonetheless, there is no fatigue limit, and this is a problem for aircraft and other things. Typical lifetime on a commercial aircraft is 100,000 hours. You go park it in Arizona after 100,000 hours, okay? It's full of cracks. Hopefully none of them have propagated to crash it, but you don't want to keep flying it, and you can't afford to repair it, but you leave it there for spare parts or for whatever reason, okay? You don't do that with ships. What do you do with ships? We used to sink them, but there's too many PCBs down in there with all the other stuff. What do we do with ships? They take them to Bangladesh and they run them aground, okay? They do. They literally run them aground on the beach, and all these little Bangladeshis go out there with acetylene torches and start cutting them up. And why do we do that? Because they're full of asbestos. And we couldn't even begin to cut up and recycle that ship in the United States because of the asbestos standards. But in Bangladesh, they have no asbestos standards. And frankly, it's almost a crime what's going on. I've read some things that a lot of the people who work on those things live for 3 years because it's not just asbestos. They're cutting through steel, and first of all, they might get crushed because they don't have a lot of safety, and someone else is cutting something over here, and all of a sudden you have 20 tons fall on top of you. But the other thing is they're cutting into old pipes that have chemicals and all kinds of things in them, that have been carried in those ships for 30 years before the ship's ready to recycle. But we tend to export our problems, our environmental problems, and that's one. And actually, there was a National Geographic thing about this, but I knew about it before. But literally, they just find a beach in Bangladesh. It's not any old beach, but they just put the motors on and head it towards shore, and it just beaches there, and people come out with all their little acetylene torches and cut it up into little pieces, and they recycle the steel and the asbestos and the sickness. Okay. So the boiler and pressure vessel code has fatigue limits. It also has it on alloy, but typically they're 2 to 5. Most of these are statically loaded structures. Why do they have a higher safety factor than the AWS D11? Yes. The consequences of failure of a pressure vessel are usually much more severe than the cost of a crack in a bridge or a building. And in fact, I can remember when I first started as a young faculty member here, there was a big brouhaha in the Federal Highway Administration because some tugboat captain who was going up and down the Allegheny River in Pittsburgh noticed that when he went down the river, the crack in that interstate highway bridge that he was going under, okay, was shorter than when he came back up. It was getting longer, noticeably longer. And when they got to it, it was like 9 feet long, okay? I mean, he could see it from, 20, 30 feet away. This was not a small crack. They ended up closing the interstate highway until they got out there to fix this thing. But it created a lot of consternation. But fortunately, bridges tend to be redundant structures. I had one in New York City once. It was the underpinning of a 20-story high-rise that if you get off if you come into New York City on the George Washington Bridge, yeah, you go underneath some buildings. Well, I got to be right up there above the highway because they found, maybe this was the 9-foot crack, they found a 9-foot crack and an 8-foot beam. The bottom flange of the beam had cracked, the whole web had cracked. It was only basically the top flange that was holding this together. And it was sort of an interesting area of New York City. I remember being dropped off there by the cabbie, and he just buzzed away, and I'm sitting there with my camera bag with $5,000 worth of equipment, and I look down and I see all these little capsules, empty capsules on the sidewalk, and I decided that's why the cab driver got out of that area so quickly. And here I am, you know, not looking like one of the natives and carrying $5,000 worth of camera equipment. Anyway, so they take me down to look at this crack underneath the building, and they were banging things as we went. The guy that was leading, I said, "What's that for?" He said, "Scare away the rats." Oh, well, this is good. I mean, okay, that's who lived down there. Anyway, so we got to the crack, and then they told me the story that when they discovered it, they had a meeting of all the tenants. This was an apartment building, and they discussed that there was no danger, but they were going to close off the highway in that particular area, and those lanes right underneath there, until they could fix the crack. And the only question they got after the tenants meeting is, where could they go get some of that crack in the basement? Okay. So there's some interesting things when you go out on these inspections. Nonetheless, the boiler and pressure vessel code, if something blows up, it can be serious, and depending on the amount of energy stored, the alloy, this factor of 5 safety on the pressure design is for ductile cast iron. Castings tend to have larger flaws than other things, so bigger safety is a factor. Factors of safety, just like the welds have more defects, larger defects than the base steel. This is for a cast vessel, okay? This is for a welded vessel with certain levels of inspection. Sometimes your safety factor, if you want to save on inspection costs and only do 10% of the vessel, you have to design to a different safety factor than if you do 100% inspection, okay? So it's a question of what's the variability, what's your knowledge of the population of defects in that thing, okay? The other safety factors, OSHA. For man-rated equipment, like scaffolding, ladders, it's a safety factor of 4. Why do you need a safety factor of 4? Well, you don't. You only need a safety factor of 2, but if someone falls, again, it's a consequence. If someone falls from 4 stories, it's not a good day. And so OSHA basically requires that anything that's man-rated, like the scaffolding, see the scaffolding going up the Great Dome behind there right now? That's got a factor of 4 safety on whatever loads are going to be placed on there. Why? Because if you go through, actually that stuff's in pretty good shape. I walk by it every morning. But I've seen scaffolding that, you know, they dropped an I-beam on it, and so the beams are bent like this before they even put them up there. And there's a lot of wear and tear on scaffolding that gets taken down and put up and stuff. And so they have bigger safety factors. But even a ladder, why do you need a bigger safety factor on a ladder? Because people don't mount the ladder on a flat surface. You know, they kind of tilt it, and therefore the stresses are higher than what they designed it for. You have to assume that people are going to do things that are not that smart. The New Orleans levees, I think Simone may have mentioned that because I pointed that out. Did he tell you what the levees were? What the safety factor on the levees is? It's 1.3, okay? And frankly, the levees didn't fail in New Orleans because the safety factor wasn't, you know, they weren't strong enough. They got breached over and they got washed away from the top. Okay, my grandfather in the 1880s was building levees in New Orleans. Okay, The X-33 space plane, I didn't bring the piece, but in some of the other lectures you'll see it because it's one of my, it's a piece of composite material. They originally designed it for a 2.0 safety factor. Well, turns out they had a manufacturing problem. And they knew they had some flaws that were not half an inch in size. They could have been 3 or 4 inches in size. So they go through and they sharpen their pencils because they have this $50 million, actually they have two $25 million vessels. Or maybe it was two $50 million vessels, I don't remember. I just remember the 50 million number. And they didn't want to declare them junk. That would not be politically a good move, okay? So they sharpened their pencils and they said, well, we don't have a factor of 2 safety, but we have a factor of 1.05 safety. So we can put them in test. This is for the liquid hydrogen tank for the X-33 space plane. And as long as we pass the test, it'll be fine and we can fly the thing. Well, unfortunately, they put them in test and it probably wasn't 1.05, maybe it was 0.95. Anyway, they failed in test in Huntsville, Alabama. And so people will play games with safety factors. That's sort of an example of a political game. Oh yeah, we're still got a safety factor. I've never known anyone who designed something with a 1.05 safety factor. Yeah.
I guess something I've been wondering with safety factors is they all kind of make assumptions, right? Like if
Yep.
you think about the buildings, you know, the Twin Towers, they were designed to spec, I believe, but
1.67.
this, you know, a circumstance that wasn't planned for gone down.
Right.
How, I guess, is that, do events like that cause safety factors to then be readjusted, or does it kind of affect?
Not necessarily the safety factor, but the design rules. For example, the Twin Towers would have been built to a safety factor of 1.67. They were designed to survive an airplane impact, and they did. It was the fire afterwards. They weren't designed. They were designed to survive fires, small fires. Fires like the combustibles in the room. They weren't designed to survive 20,000 gallons of fuel all on one floor all at once. And you can see some pictures where the whole floor is glowing red and all the beams everywhere were getting weak, and eventually it just started pancaking and going down. What happened after the World Trade Center is what they tightened up was not, they're not going to start putting more steel in buildings. You can barely afford to build the buildings anyway, right? If you start doubling the steel, you're going to, if you double the steel, you got to make not just the steel, but the windows, everything else goes up in price. I remember those were some of the arguments right after the World Trade Center. I said, well, no, everybody said, oh, we got to build stronger buildings. I said, yeah, and if you only want 1% of your population to live in a building, because they're the only ones who can afford it, okay, then that's one choice, but maybe the choice would be something else. So what they did is they improved the standards for design of egress and public announcements to tell people to get out of the building, okay? A lot of people stayed in the building for an hour waiting to see what was going to happen, and it was a little late to get out at that point, okay? If they had called the alarm and said, get out now, they would have lost fewer people. Although most of the people they lost were on the floors above. And why did they lose those people? Because they had a no-fly zone, and no helicopters could go and get those people off the roof. And so when they, for national security, they said nothing's going to go get in the sky and fly. That meant the rescue vehicles couldn't go rescue those people off the top of the World Trade Center. And most of the people who died were up above the floors that were burning. Now, another example of buildings, the Northridge earthquake, which I think was early 80s in Los Angeles. They had a fairly major earthquake out there. It turns out they didn't increase the strength safety factor. What they increased was the toughness safety factor, because buildings were supposed to be statically loaded structures, right? But in the Northridge earthquake, they all of a sudden became dynamically loaded structures as the building swaying in the breeze. I don't know, have any of you been in a tall building and seen feel the buildings swaying in the breeze? Are you kidding me? Just from wind? And go up the Prue. Yeah, I've been on top of the Prue, and you can, well, that's the elevator swaying back and forth. But I went to the Sears Tower once, and you could sort of, if you stood there on the observation deck on the 100th floor or whatever it was of the Sears Tower in Chicago, if you just stood still, you could slowly feel, the building has a natural frequency that's only a few seconds. You know, it's like 3 or 4 seconds. And then I went into the restroom on the top floor, and you could see in the toilet, you could see the water sloshing in the toilet. Okay, so you know it's moving, right? And if you've ever been through an earthquake, it actually has a frequency a little higher than the swaying of the building in the breeze. At those frequencies, sometimes the foundation, the soil can turn to jello. I mean, basically, if there's enough moisture in the right type of soil, it can just turn to something that's like jello, and things can come collapsing down. But the people had designed things for this. I got an email, was it just yesterday or the day before, from some guy in Seattle who wanted to know what he should do if an earthquake struck he's in a high-rise building in Seattle. He wanted to know if it was safe and things. I said, well, in Seattle it probably is. In certain other parts of the world it may not be, because they don't have the same types of building codes. And there were earthquakes in Chile that, was it Chile they lost a lot of people with the magnitude 9 earthquake, and Japan had another big one, and the Japanese didn't lose anywhere near as many people. But they did earlier than that. There was a 1907 earthquake or something in Tokyo that was a big firestorm. We had one in San Francisco in 1912 or whatever, and it wiped out San Francisco. Okay, they had fires afterwards, and that's when we started our building codes for earthquake protection. What happened in Northridge in Southern California in the early 80s is they had fractures. No one died because, well, I wouldn't say no one. There might have been some home or something or concrete structure that fell down on a couple of people, but the number of people who died in the Northridge earthquake, you could probably less than 100, probably less than a couple of dozen, because of anything collapsing. In San Francisco, the Oakland Bay Bridge, actually, a section of it collapsed. But I don't remember any deaths from that, okay? It's a question of how, we know how to design for an earthquake. What we didn't realize in San Francisco, not in Los Angeles and Northridge, is that when these things start swaying as rapidly as they were, not as rapidly, but as far as they were, they started getting brittle fractures because of impact loading, okay? And so they have revised the building codes dramatically. If I, well, actually, it hasn't gotten bigger. The civil engineering construction building code now, they went through kind of 2 iterations since Northridge. And so now it's, Dr. Belmar was here, he could tell me, it's, instead of the old beam formulas, which is what we did for 100 years, they now have load factor resistance design, LFRD. It's a whole new way of doing calculations for things, and it's nice if you have a computer to do the calculations for you. But it's a more sophisticated way of calculating loads. And it was because they had whole buildings that they had to condemn, big buildings, not because anyone got hurt and not because anything collapsed, but they had some of the connections that this completely broke. And some of them they could fix, and some of them it was cheaper to tear the building down. So we do improve things, but it's not always the safety factor that we're improving, I guess, is to answer your question. We look at what the real cause is, and we figure out what the least expensive way to fix it is. Okay? Hopefully. Yeah.
Factor of safety, like yesterday Dr. Belmont talked about the statistical approach to doing
Right.
right? Factor of safety never explicitly tells you what your structure reliability is, right?
That's right.
It's trying to do something similar, right? It's never reliable. Nothing is 100% reliable.
Right.
Whereas, so it's just like you have a 0.5% chance to get hit by a plane.
Right.
If that happens, then you're going to have failure, but it's only a 0.1% chance, whatever you want to call it, right? So it's just dealing with uncertainty, and then that plays into factor of safety.
Yeah, well, it is uncertainty, and what we're having is he was giving you some stuff, because I saw his overheads before he did it, from a book on safety factors in design or something like that, that goes through a big probabilistic thing. Remember, he had kind of this three-dimensional Gaussian picture and stuff. So people are now trying to apply statistics to safety factors. Right after World War II in the Liberty ships, we knew about fracture mechanics, but the big thing in the early 50s was probabilistic fracture mechanics. Okay, so you deterministic. You can calculate, you know, the fracture mechanics. You got the fracture toughness has to be greater than the stress times the square root of pi times the crack length. Well, that they had known since 1925. Okay, and that's a deterministic formula. Okay, you can plug the numbers in, and you can get a, you know, is this greater than that? But people started thinking about, well, designing things and having a whole fleet of aircraft is really a situation of probabilities. And so now people, when they look at safety factors, they're saying, well, we should do some probabilistic design. The thing is, now you're taking something that was very simple. Do I have a safety factor of 2 or 1.67 that even you and I can calculate? And now they get in to, you now have to hire a PhD in statistics to tell you what your safety factor is. Okay, well, it's good for the statisticians, okay, full employment for the statisticians. And it is useful for calculating, estimating what your reliability, probability of failure is. But it's still the problem of, I always say, you know, we can talk about the probability of being hit by a car crossing Mass Ave. And that's fine to talk about probabilities, but if you're the one hit by the car, it's 100%, right? And so a lot of this probabilistic safety factors, to me, is just taking something that's simple enough to be understood and used and turning it into something that's too hard to use. I mean, that's a personal opinion about that stuff. We do get more sophisticated about it. It turns out that my best friend, when I was, you know, 5 and 6 years old, living in Atlanta, Georgia, was from Norway. And he showed up in my office about 15 years ago because he, you know, I have an unusual spelling of the last name, and somehow he had come across me, and he was in Boston, and he showed up. I hadn't had contact with him since I was 10 years old. But so we started talking. I knew his father worked at Martin Marietta, where they made the C-5A and did all this Air Force stuff. But his father was brought from Norway about 1950 because he was one of the world's experts in the new field of probabilistic fracture mechanics. And when he was working on it in the early 1950s at Lockheed Martin in Georgia, or Lockheed Corporation in Georgia, it was all classified work. Okay, this is something the Air Force was trying to figure out the probability of whether the planes could fly. Okay, well, I'm not sure if most of the pilots would feel good about knowing that they have a probable chance of flying, unless you're a test pilot. Those guys, that's what they're all. That's what it's all about, is the probability of whether you're gonna, you know, whether you're gonna have the same number of takeoffs and landings, okay, or controlled landings, or whatever you want to call it. But that's what test pilots are all about. Okay, so I don't know if that really answers your question. It tells you my cynical view about trying to complicate a simple concept and making it so complex that few people can understand it. It's sort of like the tax code. You know, who understands the tax code? It's so complex. In any case, the couple of points I wanted to make, though, let me say, well, actually, maybe we will. Dr. Belmar is going to give his last lecture on Tuesday, and I've got enough things I didn't talk about today that we'll go ahead and have class on Monday and Tuesday. Those will be the last two classes. Okay, that will be the simplest way to do it. And if you haven't told me what you're going to, which modules you're going to take, or what I think. Marissa, I'm not sure you've given me that, okay? And Steve, I'm not sure you've given me. Have you? Okay, well, there's two things. I need to know which modules of the different, the next two modules that you're going to study for the class. Yeah.
I was curious, and I think maybe a couple other guys have questions. If, depending on the other two modules we choose, do we still just give one presentation?
Yeah. You give one presentation, and